I am Vimala, Assistant Professor, Department of Computer Science, working in St.Josephs College of Arts and Science for Women, Hosur. My topic is 3D weaving from subject Computer Graphics. In the computer graphics, we are going to see about weaving pipeline, that is three-dimensional weaving. And first topic, that is weaving pipeline. The three-dimensional weaving pipeline is a series of stages that transform a 3D scene into a 2D representation for display on a 2D screen. This process involves several steps to convert the spatial information of a 3D scene into the appropriate 2D coordinates for rendering. The pipeline typically consists of following stages: modeling transformation, world transformation, weaving transformation, projection transformation, clipping, viewport transformation, and scan conversion. First one, modeling transformation. This is the initial stage where the 3D model is defined and manipulates in its own local coordinate system. Geometric transformation such as translation, rotation, and scaling are applied to the model to position and orient it appropriately in the 3D world. Next, world transformation. The model objects are then placed in the world coordinate system. This involves combining the modeling transformation with any global transformation that affect the entire screen. It establishes the relationship between different objects in the scene. Weaving transformation. In this stage, the scene is transformed from world coordinates to camera or weaving coordinates. The camera represents the viewpoint from which the scene is observed. The weaving transformation includes operations like translation, rotation, and scaling to position and orient the scene within the camera coordinate system. Next is the projection transformation. After weaving the transformation, the 3D scene is projected onto a 2D plan. That means even though it is a three-dimensional view, it should be projected on the two-dimensional view screen. So this is the projection transformation. This is typically done using perspective or orthographic projection. Perspective projection is how objects appear smaller as they move away from the viewer, so creating a sense of depth. Orthographic projection, on the other hand, maintain parallel lines and is often used for technical drawings. Clipping. Next stage is clipping. In this stage involves removing any part of the screen that are outside the weaving window or weaving boundaries within the portion of space visible to the camera. Clipping ensures that only the geometry with the specified weaving value is considered for rendering, that is, which is within the boundary will be saved and others will be discarded, same as we see in the 2D. Again, next stage is the viewport transformation. The that means the projected and the clipped scene is then transformed to fit with the dimension of the 2D display known as the viewport. This stage involves scaling and translating the coordinates to map them onto the screen space properly. Now scan conversion. Finally, the 2D coordinates are converted into pixels for display. This involves determining which pixels are covered by the 3D objects and assigning appropriate color or texture to these pixels. Next is the weaving coordinates. We know in the two-dimensional we have two coordinates x and y. In the three-dimensional we have three coordinates x, y, and z. So we have been seeing the three-dimensional weaving coordinates. In the three-dimensional weaving coordinates we have three coordinates x, y, z. X coordinate represents the horizontal position of a point in a space with positive value extending to the right and negative values to the left. Y coordinate, this represent the vertical portion of a point in space with positive values extending upward and negative values downward. Z coordinates, this represent the depth or distance from the viewer along the line or side. Positive value extend into the screen while negative value extend outward. These three coordinates uniquely define a point in 3D space. In computer graphics, these coordinates are used to represent the location of vertices, that means corner of 3D objects. To transform and manipulate 3D objects, that is 3D objects, in a computer graphics system, various transformations are applied to the coordinates. The process of representing 3D objects on a 2D display involves a projection, which is typically done using mathematical techniques such as perspective projection or orthographic projection. This projection converts the 3D coordinates into 2D coordinates suitable for display on a computer screen. Here we are going to see about the projection. So far we saw only a weaving coordinates. Now we are going to see about the projections. After all the weaving process, how we are going to project the three-dimensional object in a two-dimensional surface. So first projection is a parallel projection. Parallel projection is a method used in computer graphics to represent three-dimensional objects on a two-dimensional surface. In three-dimensional parallel projection, the projection lines are parallel to each other, resulting in a realistic representation where objects maintain their actual proportion and shapes. There are different types of three-dimensional parallel projection, and one of them is the orthographic projection. In orthographic projection, the projection lines are perpendicular to the projection plane. This means that lines of sight are parallel, creating an image where all parallel lines in the 3D space remain parallel in the 2D representations. There are three types of orthographic projection. First one is isometric projection. In isometric projection, the object is rotated about specific axis to align its principal axis with the axis of the projection. This results in all three dimensions being shortened at the same rate. Isometric projection is commonly used in technical drawings and computer-aided design to represent three-dimensional objects. Another next step is diametric projection. Diametric projection is similar to isometric projection, but the scaling along 2 or 3 axes is different. In diametric projection, 2 of the 3 angles between the axes are equal, while the third angle is different. This type of projection can provide a more natural look for certain objects, and sometimes it is used for artistic purpose also. Next, trimetric projection. Trimetric projection is a form of parallel projection where all 3 of the angles between the axes are different. Unlike isometric and trimetric projection, trimetric projection allows for more flexibility in choosing angles, which can be adjusted to better suit the characteristic of the object being represented. Trimetric projection is not as commonly used as isometric projection, but offers more customization options. Next is perspective projection. The three-dimensional perspective projections are methods used to represent three-dimensional objects on a two-dimensional surface in a way that stimulate the effects of perspective as it would be perceived by an observer in the real world. These projections aim to create more realistic and natural appearance. There are two main types of three-dimensional perspective projection. One is linear perspective, another one is atmospheric perspective. Linear perspective, one-point perspective. In one-point perspective, parallel lines in the three-dimensional space converge to a single vanishing point of the horizon. This method is often used when the viewer is looking directly at one face of an object or is seen, and the primary vanishing point is aligned within the viewer's line of sight. Two-point perspectives. The two-point perspective involves two vanishing points on the horizon. It's commonly used when the viewer is looking at an object or seen from an angle and not directly facing of its faces. Two-point perspectives allow for a more dynamic representation of objects with multiple visible faces. Three-point perspective. In three-point perspective, there are three vanishing points, two over the horizon and one above or below it. This type of perspective is useful when depicting objects from extreme angles, such as looking up at a tall building. Next, atmospheric perspective, also known as aerial perspective. Atmospheric perspective takes into account the effect of atmosphere and the appearance of objects at varying distance. As objects move further away, they tend to appear lighter in color, less distinct, and may exhibit a shift in color towards blue to atmospheric scattering. Atmospheric perspective is particularly relevant in landscapes and outdoor skiing. It adds depth by simulating the way distant objects appear hazier and less defined compared to closer objects. Thank you.